Hello, today we're going to look at some exponential and logarithmic functions. You have your keywords presented at the top. There is a lot of them. Once again, this is a pretty heavy vocab section, but each one isn't so bad. So let's start by looking at an example where you would use exponential functions. So we have an example here that involves cells. So it says, suppose you have one cell in a dish and it splits every day. How many cells will you have in 100 days? So what we have here is we're going to start here on day 0, and we're going to start with just one cell. I know my cell looks like a 0, but this is really just one cell. After 1 day has passed, this cell is going to split into 2 cells. After 2 days, well, each of these cells is going to split, and I have 4 cells total. On day 3, well, more splitting and less drawing. It's going to be a lot of circles. I think I got them all. We have 8 cells. And while we could continue to do this, it would be a bit of a pain. We could keep going to see what happens. And we could even make a really nice looking table here. The issue is that this is still going to take a long time to figure out what happens in 100 days. So instead what we want to do is we want to come up with the pattern here so we can make a nice formula to help us solve this problem in a much more efficient way. And what's going to help us out here are called exponential functions, because what exponential functions are good at is measuring proportional change. In this case, we're doubling the previous day's numbers of cells, and the general formula for an exponential function is that the future value is equal to rate times a time. And we can figure out this function by looking at what happens. So on day 0, we just have one cell. On the first day, we double the cells. On the second day, we take 2 times the previous day's cells. On the third day, we take 2 times 2 times 2, so we double again the previous days. On the fourth day, we double again. And we want to think about, well, what's the shorthand for each of these numbers? So the shorthand is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. So that means the formula we can write is that the number of cells on any given day t will be equal to 2 to the t. So what this actually lets us do is it actually lets us figure out that, well, after 100 days we're going to have 2 to the 100th power cells. Now this is some ridiculously large number. It's pretty unlikely that we're going to get that many cells, but it's a good example. So now we're under our first technical definition of exponential functions. If we let a be any positive real number, then any function of the form f of x is equal to a to the x, so a number raised to a power, will be called an exponential function with base a. So the function we had on the previous page, c of t equals 2 to the t, certainly fits this pattern and is a good exponential function. Now the key to working with exponential functions and exponents is really remembering what exponents mean. So remember that if you write the 3 times 2, what this really means is you're adding up 2 3 times, and both of these will give you 6. And then we want to remember that 2 cubed really means 2 times 2 times 2. So in this way, what we want to remember is that multiplication is a fancy way to say repeated addition, and exponents are just a fancy way to repeat multiplication. They're just shortcuts to help us along. Now there's also this neat thing called repeated exponentiation, which is called tetration, but that's for a different course. Don't worry about it. Now, just like there's repeated rules for multiplication, there are some good properties to remember for exponents, some ways to manipulate exponents when you see them, and we will review a few of them now. Most of these should be pretty familiar rules to you, but you probably want to take a second to review a little bit. So let's go through a few of these. Rule 2 up here says that what we can do is the shortcut, if we have a to the x times a to the y, we can add our exponents. Now we want to remember, why is this true? Well, this is true because what does 2 cubed times 2 to the 4th really mean? Well, the 2 cubed part really means 2 times 2 times 2. The 2 to the 4th part really means 2 times 2 times 2 times 2. all together now we have 7 2's that we're multiplying together, and that's the same as if we would have added the exponents. In a similar way, number 3 up here tells us a way in which we will multiply exponents if they're raised to the powers. And once again, if you ever forget this property, you just take a second to think through what's going on here. Well, if you have a 2 cubed, and then you have the squared on the outside, what the squared means is that there's really 2 cubes being multiplied together. This is repeated multiplication. Each of these 2 cubes stands for 2 times 2 times 2. And all together, what do you have? Well, all together, there's 6 2's, which is the same as if we would have multiplied the numbers. Now, if you mess this up, and you try to add them together, you'll end up with 2 to the 5th, and you'll see that this is not right. So always, if you ever forget these two rules, and I think they're the most common rules people sort of conflate together, just take a second to remember and really think through with an example what would have to be. It's a much better use of time to think through what should happen rather than try to move too quickly and just guess at which one to use, rather to multiply or add. So the last property we're going to look at is property 5 over here. Now I'm saying it's the last one we're going to look at in this video. You should know how to do them all. But what property 5 tells us how to do is a shortcut when we have one exponent over another exponent. And then once again, it's just about thinking through what do they mean. Well, 2 cubed means we've got 3 2's in the numerator. 2 to the 4th means we've got 4 2's in the denominator. And then we can start canceling. You know, we cancel this 2 with this one over here down there, the middle one with the last one. In the numerator now, the thing that we're left with is, even though we've gotten rid of all the 2's, there's always a secret multiplied by 1 up there. So we get a 1, and we're left with 1 2 in the denominator. And the way we write this is 2 to the negative first. Negative exponents indicate how many you're multiplying by in the denominator. And hopefully what you've noticed here is that rule 7 up here is given incorrectly. This should really be 1 over a to the x power. The negative just means move into the denominator. And so we could have done rule 5 quickly by just saying we need to subtract these exponents because they're going to cancel with each other. So that's how most of these exponent rules work. We're going to do a bit more practice with these though. So what we have here are some properties of exponential functions, and what I've graphed down here are what all graphs of exponential functions usually look like. And really the only difference between them is whether or not in your exponent you have a positive number or a negative before your exponent. In the positive case, we'll be over here on the left hand side, and in the negative case, we'll be over here on the right hand side. Without a negative in the exponent, as we move to the right, we're going to increase. With the negative in the exponent, as we move to the right, we're going to decrease. However, they share most of the same properties in common. So the domains for both are negative infinity to infinity. You can put any real number you want in the exponent, and you're going to get a number back out. The range for both of them is going to be from 0 to infinity. We're only going to get positive numbers out from exponential functions. If you try to compute, say, 2 to the 373rd, and you somehow get a negative number, you've done something wrong, okay? Something went awry. Try again. Both of them happen to hit the same y-intercept. They both hit the point 0, 1. And finally, both of the functions are 1 to 1. Now remember back to when we talked about inverse functions. This is a really important thing because property 4, since they're 1 to 1, these have inverses. And that's going to be incredibly important for what happens next. And now for something completely different. What we're going to look at here is the number e. So the number e is approximately equal to 2.71828182846. It's defined as the number that the expression 1 plus x to the 1 over x approaches as we make x closer and closer to 0, and we call the function f of x equal e to the x the natural exponential function. Now I'm sure some of you at this moment are thinking WTF, which of course stands for only one of two things. Wow, That's fantastic. Or possibly, what's this for? Most of you are probably, of course, in the second camp thinking, what's this for? You probably saw the number e introduced at some point in high school, and like most people, it was given to you as a number, you were told it was important, not a lot of detail about it. So now we're going to give a little bit of the background about why this number is so important. So suppose you decide that you have $1 and you're going to invest that dollar at 100% interest for 1 year, and at the end of that year you're going to have $2. 100% interest means at the end of the year you're going to get back exactly what you started with, so you're going to have $2. Great job on your investment. Now, most people won't actually take this investment, but we're in a math class so we can do silly things like this. However, most places don't pay interest just at the end of the year. They pay you interest occasionally throughout the year. So instead what could happen is you invest your dollar at 100% interest for 1 year, but you take half the interest after half the year, then the rest at the end. And now what's going to happen is now you're going to collect interest on your interest. What's going to happen is that after 6 months, you're going to collect half your interest, so 50%, so you're going to end up with $1.50. And now what you're going to happen again 6 months later is you're also going to collect 50% of your $1.50. And so what you're going to do is you're going to collect half times your $1.50 plus your original $1.50 to give you a grand total of $2.25. Now, this was sort of a strange way to write out this problem, but what really happened is that you started the year with $1, you multiplied this dollar times 1.5 to get your first $1.50, and then at the end of the year you multiplied it again by 1.5. So you took your $1 times 1.5 squared to collect your interest twice throughout the year. Now let's see what happens if you do this again. So now instead, suppose you decide to collect your interest every month, that is 12 times a year. Well, what you're going to earn is you're going to take your original dollar, you're going to multiply it by 1 plus 1/12 of the total interest. So this is your interest payment every month, and you're going to do this 12 times to end up with 2.613035. Okay? So you're making more money as long as you're collecting your interest more often, because then you're also gaining interest on your interest. Now we're going to do this very abstractly. We're going to say, well, you're going to demand an interest payment now n times a year. So in total, you'll take your dollar, and you'll multiply it by 1 plus this little partial interest term, 1 over n, and you're going to do this n times a year. And now what we're going to do is we're going to do something crazy. We're going to say, well, what happens if this n gets very big? I'm not talking about 12, 100, I'm talking if you call it billions, trillions. I'm saying if you take this n and make it infinite, so you're collecting interest on your interest all the time at every moment. This is called continuous compounding. And what will happen here is that as n grows very large, this number will approach this fancy number e. So this number e, what it really represents is it represents the idea of how much money you can make if you collect interest on your interest continuously. So this number e is a very natural choice for anything that grows continuously. E is useful in banks that collect interest. E is also useful when modeling population growth or radioactive decay. It's a very natural choice to use for things, and that's why it's just used very often in math and in science. So just a brief history now. As we said, E is approximately equal to 2.7182818, and it's named after this mathematician we have here named Leonhard Euler. Euler lived in the 1700s, and he lived in mostly Russia for most of his life, though he's originally from Switzerland. And he's widely regarded as the most prolific mathematician ever. He wrote more math than anyone else before or after him. And actually, during the last about 20 years of his life, he was blind in both eyes and still continued to do mathematics, produce more math than anyone else. What he would do is he would have his students read to him. He would think about stuff, and then he would say stuff to them that they would have to write down. He had a terrific memory, and was able to produce a lot. In fact, he was so prolific and so famous in Switzerland that they put him on his money. So he's actually one of the only mathematicians ever to be put on money, but it's a pretty neat honor, and he's a good mathematician. Also, Euler today is going to be your secret keyword you're going to need in the quiz, so make sure you remember the name Euler. Even though it's spelled weird, it is pronounced Euler. So next we're going to talk about the natural logarithm function. As the function f of x equals e to the x is 1 to 1, it's a good exponential function. We discussed previously that it must have an inverse. So if x is any positive real number, we can define the natural logarithmic function, denoted by ln of x, as follows. ln of x equals b if and only if x equals e to the b. So we pronounce this function by ln of x, or the natural log of x. So the key here is that this is an exponential function's inverse, okay? So it reverses the inputs and outputs from the function e to the b. So a quick note for the language nerds in the room, like me, the reason we write it as ln of x and not nl of x is that it comes from a Latin phrase, logarithmus naturalis, where the adjective occurs after the noun. This is very standard in Romance languages. You say the noun first and then the adjective. In English, we like to put the adjective first and then the noun. So that's why it's written ln and not nl, even though it's the natural logarithm. Another good way to think about where this happens in the real world is to think that an exponential function takes as input usually time, and it gives out the value of whatever is being measured at that time. So for instance, in our example of cells, what happened is that the input was the number of days, and we put that into an exponential function to figure out, well, how many cells do we have at a certain day? Whereas logarithm functions reverse this. A logarithm function, you're going to input the value being measured, and it's going to tell you how long it takes to reach that value. So the logarithm value as an inverse reverses this process. It takes in the value as an input, and as output tells you how long a time to reach that value. So as a quick example, what this means is that natural log of 1 equals b. Well, we don't know what b is, but what it means is it's asking the question, what should b equal so that e to the b is equal to 1? So this is the question it's asking. It's asking, what exponent do I use in e to the b equals 1 to make this true? And so what has to happen is b has to be 0. So that means the natural log of 1 has to equal 0. So let's look at here at some properties of this natural logarithm function, which we're going to be using a lot this semester. So down here, what I've graphed in the purple color is the exponential function, e to the x, whereas in the more orange color is our inverse function, the natural log of x. And we can see that it is an inverse because we've just reflected along this line y equals x to get our new function. The point 0, 1 was on our e to the x function, so 1, 0 is a point on natural log. 1e is a point on our exponential function. That is, if I put 1 in for the exponent, I get e out. So e1 needs to be a point on our natural log, and we've mapped them all over by flipping them. And we can record some properties here. Well, the domain of the natural log of function has to be 0 to infinity, because this was the range before of e to the x. The range of the natural log function is negative infinity to infinity, because this was the domain of e to the x. That is, we've just flipped range and domain with inverse functions. The x-intercept of the natural log is 1, 0, since this was the y-intercept of e to the x. And of course, this function is also 1 to 1 because it has an inverse. I mean, that's the big key to natural log and e to the x, is to remember that they're going to be inverse functions. The natural log of e to the x is x, because if we compose the functions we get back what we started with. E to the natural log of x also has to be x. They're inverses. So last, we want to just discuss some properties of logarithms that will be useful as we go about solving problems. So over here on the right side, what we've got in properties 4 and 5, these are just our inverse properties. So these are just true because when you compose a function with its inverse, you should get back out what you started with. That's why the natural log of e to the z equals z, e to the natural log of x has to equal x because they are inverse functions. And before we go about using these other properties 1, 2, and 3, let's think first a little bit about why they make sense. So natural log of 4 really means how long will it take to have 4 times what I started with. So remember we talked before about what this really means. Natural log of 4 is going to equal a value. It's going to equal a time. And what this time is this is going to be the exponent. I need to put in the e to the b so I get out 4. So this means if I invest $1, how long until I have $4? Well, the natural log of 4 is going to be equal to the natural log of 2 plus the natural log of 2, since 2 times 2 equals 4, and what we're using up here is property 1. Property 1 says that we convert multiplication here into an addition problem. And why does this make sense? Well, this makes sense because this says if you want to have 4 times as much money, well, what you need to do is you need to double your money once, plus you need to double it again. That is, to have 4 times as much, we need to double, and then we need to double what we've doubled so that we have double again. So in this way, it sort of makes sense that an exponential problem converts this problem of multiplication into a problem of addition. That is, we need to add up those times we had before. What we may also do is we can also prove it very, very abstractly. What we can say is we can say, well, let's let m equal the natural log of x, and let's let n equal the natural log of y. Well, we remember what these really mean is what this really means is then e to the m is equal to x, and e to the n is equal to y. Because they're inverse functions, we switch the inputs and outputs. So what this means is we can write now that e to the m times e to the n is equal to x times y. Now you could be saying to yourself, how in the world is this getting me closer to what I wanted? Well, what we can do now is we can take the natural log of both sides. So now we have the natural log, and I'm going to do something bad. I'm going to swap them, but it's okay, is equal to the natural log of e to the m times e to the n. But, well, what do we know? What we know is one of the things we can do with exponents now on this side is we can add them. So this is going to be equal to natural log of e to the m plus n. And what do we know? We know that this is an inverse function, so the natural log of e to this something is just going to end up being just that something m plus n, which is equal to the natural log of x plus the natural log of y. So what we've got now is we've got our equation. The natural log of x times y is equal to the natural log of them in exponent form. We can add exponents. It's an inverse function, and so we've converted from this multiplication problem into an addition problem instead. In a very similar way, we can look at property 2, which converts a division problem into a subtraction problem, and property 3 converts an exponent into a multiplication problem. So now that we sort of understand these rules a little better, let's see how we can use them to help simplify equations. So one thing we might want to do is expand the following equation. And so what we can do first is the first thing we're going to do is we're just going to rewrite this in terms of, instead of that square root symbol, we'll make it into an exponent. So the square root is the same as the exponent 1/2. And then what we want to use is just a property of exponential functions, says that we can now distribute this 1/2. And so distributing the 1/2 gives us 5 to the 1/2 times x to the 1/2. So this is just exponent property. The next thing we want to do is now we want to look at our natural log properties. And so what we should do is we should be looking for, in terms of our exponential functions, it says to simplify we need to either look for multiplication, division, or an exponent. And here what we have first we have this multiplication on the inside. I know there's exponents, there's the 1/2 there, but we need to wait till the end to do those. What we need to do first is we need to do first the multiplication property. Because what we have is we have one quantity multiplied by another quantity first, and so it fits the first pattern better. So using the first property of natural logs, we can break this into two natural logs. The natural log of 5 to the 1/2. The multiplication becomes addition to the natural log of x to the 1/2. And now when we look at this, now is the good time to use that 1/2 property. What we can do now is we can pull a 1/2 out of both of them using property number 3. And of course I didn't leave room for the 1/2. And there we've expanded it. So this step here was by property 1, the multiplication, and the last step was using the exponent. And this is what it means to expand. Basically, make the insides as simple as possible. So this is simple inside parentheses. Let's look at a few more examples of this. So let's try to solve our equation here. The natural log of e to the 2x equals 12. When we want to think for a second, well, what should we do first? Now the first thing, some people might be tempted to use rule 3 here, and there's nothing wrong with rule 3. You know, we definitely have an exponent up there that we could bring out. But what we can do even faster here is we want to remember something very important. The natural log of e to the anything, and I should have chosen a better symbol, I'll never be able to draw it the same, is just that anything, okay? So a little better. Natural log of e to the w is equal to w because they're inverses. Natural log of e to the something that actually looks like a w is something that actually looks like a w. So what we can do here is we can simply say that since they're inverses, what we'll have really is the equation 2x equals 12, which by some simple algebra dividing both sides by 2 leaves x equals 6. Really, this problem definitely looks a bit more complicated than it really is. Let's do one more that actually is a little more complicated. Now let's look at the problem natural log of x squared equals 8, and we want to figure out exactly what x needs to be. So what you should do here is pause the video, take a little bit of time, and try to solve this problem, and then come back to it. So I'm going to show you exactly what I did the first time I tried to solve this problem. I said, well, this looks like a great candidate for property 3. We have an exponent up there. So what this means is I can rewrite this whole equation as 2 times the natural log of x is equal to 8. Divide both sides by 2. Leaves the natural log of x is equal to 8 over 2, which becomes the natural log of x is equal to 4. The key here to remember is that what I can do is I can take both sides to the e power, so e to the natural log of x is equal to e to the 4th. As they're inverses of each other, this means that x is equal to e to the 4th. And I thought to myself, this looks great, I'm done, I'm good to go. So one of the things we always want to look at is we always want to check the graph before we start solving something to see how many solutions we should expect. Remember, we got this one solution here that x is equal to e to the 4th, and e to the 4th is right there, so this is fine. We got this one solution over here where the graph of our function seems to hit 8, because this is just the graph of y equals the natural log of x squared. The problem is what's this thing over here doing? That looks like another solution. Why didn't we get that solution as well? And the reason we didn't get that solution is because we can only move this exponent out in careful cases where we're sure that what's left, the x, is positive. So let's look at another better way to solve this problem. So instead of using the properties right away, what sometimes is a good idea is to exponentiate first. So instead what we'll do is we'll take both sides, e to the natural log of x squared is equal to e to the 8th. And since e and natural log are inverses of each other, what we're left with on the left side is just x squared is equal to e to the 8th. And now here's the key thing: whenever you have x squared equals e to the 8th, what we need to remember is that there's going to be two answers. What we need to do is we need to write that this is x is equal to plus or minus the square root of e to the 8th. So this is plus or minus e to the 8th to the 1/2, which is plus or minus e, and now we know what can we do with the exponents. Good, we multiply them, correct? Plus or minus e to the 4th. So we really have these two solutions here to this equation, not just one. So there are going to be some problems that are posted on Blackboard that you should try for class tomorrow or whenever you're watching this video. But of course, if you always have questions, please see me during office hours, send me an email, or ask in class.